Okay, so I hope to finish grading the exam today. Probably I'll get. I already finished the first half of the exam. So I think like the sketching problem was pretty well, went pretty well. The one about the absolute max and mean, yeah, that was relatively okay. The one that was had a little bit of issues was optimization problem. So I think, yeah, probably the exam grade will be a bit lower on this exam compared to the first two, which is fine because kind of like this is like I think the third midterm is the one that has like the most difficult topics of the entire course, so that's okay. Well, what I'll probably do after I finish grading the exams, I'll send you like the usual announcement, send you the solutions for the exam, but I'll send you like a letter grade that includes like your three exams so that it is a little bit more accurate because like you did pretty well on the first two exams and this one's like the scores will be a bit lower. So that should even out. But if I just send like a letter grade for the third exam, that could be a little bit confusing. So I'll send you that information later. I'll definitely finish the grading today. So in a couple of hours, I'll send you that information. But yeah, yeah, I think the topics in the in this exam, I still have to check the second part, as I said. So I'm not 100% sure how you did there. But I mean, yeah, this is like there's like a local max in terms of difficulty for the exams, which is the third one. The only thing that's left will be the final next week, and the final it is a final exam, so there will be stuff from the first like I'll give you more information about the final, I guess, later this week. But there will be some problems which are just like problems that you could have seen either on the first midterm, the second midterm, or this midterm. So it's like more like a mixed bag. So I do think like because of that, it's probably a bit easier than this exam because the topics on this exam are just a little bit more tricky. But yeah, I'll try to create some practice exams and other things for the final this week, and we can talk about it. I mean, on Thursday, I think that could be a good idea. My plan is to. I mean, we're not we don't have that many topics left. We're almost done with the course material, so we could, if things go well, we probably will finish the material for the course either Thursday of this week or Monday of next week, in which case, like, um, you know, on Tuesday and Wednesday, we can do something else, like maybe you just ask me questions or we work on certain problems, things like that. But I don't want to, cover material for the final the day before or on Tuesday. So I'm aiming for finishing everything by Monday, but we could finish things a little bit earlier. So that way you have some time to to go over everything over the weekend. Yeah, like we have very few things left actually. So I'm pretty confident. Um, so my plan was to break it. The final it is scheduled for 3 hours. So I was planning on breaking it into 4, 4, 4, like meaning four questions, four questions, four questions. That's what I was. I mean, but I want to, the probably each part would be a little bit longer, like 45 minutes instead of 40. And like one of the questions would be something more like a true false question or something like that. Not so having a question where you don't have to like do a lot of calculations, more like more qualitative question. Oh, but yeah, and no more than four. I mean, probably 12 questions then uh, on the final. But yeah, it's broken into it is broken into 3 hours. So I have to just check that thing because I suppose like the easiest thing would be to do it from 1 to 4 so that people have time for lunchtime and so I guess that would be the idea. But yeah, once I finish the details I can let you know on Thursday for sure. You should think about it. I guess I would think about it as like a midterm plus other stuff. So meaning like there will be at least 6 questions that are completely new, like on the stuff about integrals that we're doing. So kind of like as if you had like a midterm, but then there would be some other questions like the other half would be kind of like previous stuff, old stuff. And that's kind of how I'm trying to build it up so that it's like so that it doesn't like the new stuff doesn't like occupy more than 0.5% of the exam itself. Okay. Mm, let's see. So today we're going to start getting into the stuff about finding like the integrals in a more systematic way, which we haven't done. So just to I mean, it has been a while because the last class we had it on Thursday. So just to give you like a reminder of what we were doing, like let's just go back into the notes to see what we were doing. So like in the typical examples that we were doing, like somehow like if you wanted to find like an integral like this, like the integral from 0 to 1 of x squared dx, like what we did was a little bit kind of complicated. What first we would change the upper bound into a variable so that we would get a function, and then the fundamental theorem of calculus said that this function had derivative equal to the stuff inside the integral. So like the problem, once we did that, the problem became about finding a function whose derivative was the function we were integrating. And that's kind of like the important thing that we have to go after now. So the idea, like, so let me just try to summarize what the strategy is. So like the idea is like you want to find something like, so you want to find like like you want to find like an integral like this. And so if you just check what we were doing last time, that requires you finding this integral requires you to find a function meets requires you a function whose derivative is f of x, whose derivative is the function you're integrating. That is f of x. So again, like the base, you'll see that once we have that, the problem will be complete more or less. So we can call like this function usually is called an antiderivative for f of x. Okay. And it is denoted by f of capital uppercase F or string. Okay. So I'm about to give you some examples. And like this, this will soon clarify the meaning of antiderivative. You'll see why. So, but you'll see it's kind of like the reverse problem to finding a derivative. So it's nice to kind of do a diagram, like in some sort of diagram. So that's what I'll do in a second. Let me use two colors to make this more clear. Okay, so imagine that I start with the function. And this diagram means that I'm going to take the derivative of this function, right? So the derivative of this function, I suppose, right, like probably you remember that it's 3x squared, right? So you get this. Now, imagine that I now imagine that I gave you, I start now on this end. So I give you like the function 3x squared, right? And I'm asking you to find, right? To find a function whose derivative is 3x squared. So I'm trying to go backwards, you see? So like if I start with 3x squared and I asked you for a function whose derivative is this, I would have to say x cubed, for example. So in this diagram, if you want to go backwards from the derivative to the original function, that going backwards is what we're calling the antiderivative. And it's called antiderivative because it's literally reversing the effect of the derivative, you see? So what you write is something like, you would write something like this. This is called the antiderivative of derivative of 3x squared. And this is like the functions with derivative 3x squared. And the functions that have derivative 3x squared are x cubed, right? Because if you take x cubed, you get, if you take the derivative of x cubed, you get 3x squared. And I don't know if you remember that there was some, this is not, it's almost the answer, but there's just like a subtle point here where it is not just this, there's still some freedom left here. Anyone remembers from last time what else you could put here? Yeah, plus a constant because plus c. So that's usually how it's written out. Because what this means is that if you take the derivative of x cubed plus a constant, you still get 3x squared. So kind of going backwards is fine. It gives you what you were expecting, except that maybe you get like an extra constant around. So here c is here like an arbitrary constant. Is that making sense? So what you end up writing, what you would write here, like it's literally that. Like that's kind of how people will write this. What people will write is that like the derivative of 3x, like sorry, the indefinite integral or the antiderivative of 3x squared dx is x cubed plus a constant. Is that making sense? Okay, let's do just to check if this is okay, let me put it like this. This is actually how you should think about this problem. So let's put. So now imagine that I started on the right side, right? So I start with x plus cosine of x, okay? So I kind of start on this end, and I'm asking you to see what we should put here. What do we need to put here so that when you take its derivative, you get x plus cosine of x, right? So what should go in here so that its derivative is x plus cosine of x? What do you think the answer should be? Right. X squared over 2, I mean, that's kind of like what makes this a little bit tricky. You kind of have to think backwards, right? So x squared over 2, we knew x squared over 2 would have derivative x, right? And then on the other hand, like sine of x has derivative cosine of x, right? So this is already giving us like the correct formula. And then anything else that differs by a fixed number plus c will still continue to give you the correct value because the derivative of a constant is just 0. So you can always add plus 0. So the reverse process, right, like of finding a function whose derivative is x plus cosine of x, it's just x squared over 2 plus sine of x plus c. So what you would like to write, and again, obviously I will give you some rules that helps you find this out. What you would like to write is that the antiderivative or the indefinite integral, of x plus cosine of x is x squared over 2 plus sine of x plus c. Okay? But I'm just trying to convey the idea that it is like going backwards, right? So when we had like the function, we already learned how to take its derivative, right? So we have gone from function to derivative, right? Now we're going from the derivative itself to like a function that could have given us that derivative. I mean, it's not a perfect analogy, but it's like, if you had like two substances, you mix them together, right? You get like this mixture. It could be a mixture of paint or whatever. So kind of mixing them together is in a sense like the derivative. And now what we're going to do is kind of try to find like the process that would kind of break them apart and undo the effect of the combination. So the antiderivative is kind of built so that it kind of cancels out what the derivative did. Is that making sense? And then maybe just to get ahead of ourselves a little bit, I mean, all of the today we'll spend like kind of finding antiderivatives. But what's the point of an antiderivative? The point of an antiderivative is once you have that, then you can really just evaluate the integral. So how if you know an antiderivative, then an integral of from a to b of f of x dx, it is just really the antiderivative evaluated at a at b minus the antiderivative evaluated at a. Let me put this in different colors. So once you have an antiderivative, the formula for these definite integrals is very, very easy. You just like literally take the antiderivative and evaluate it at the endpoints and subtract the answers. Okay. So I'm about to show you what I mean by this. So for example, if you wanted, we already found, we had already found like the antiderivative for 3x squared, right? So imagine that I had wanted to find I want to find the integral. Let's put a 3 here. Let's put like 1 here. So imagine I had wanted to find the integral from 1 to 3 of 3x squared dx. Okay. What this is saying is that take the antiderivative of this, of 3x squared, which was x cubed plus c, right? And evaluate it when x equals 3. So we're going to, I mean, usually this is replaced with a vertical line. Maybe I should put it like as a vertical line because that's typically how it's written. So what this means is that I'm going to take this expression and plug in x equals 3 here. And then I'm going to do the same at the bottom. So I take the antiderivative. The antiderivative was it was x cubed plus c. So I evaluated at 3. I evaluated at 1, and I'm going to subtract the answers. Okay. So again, this vertical line just means that you're going to evaluate. Oops. Let's see. So when you evaluate at 3, what do you get? You get 3 cubed. 3 cubed is 27, right? So you would get 27 plus c minus, what do you get when you evaluate at 1? You get 1 cubed, which is 1 plus c, right? And so what do you get overall? You get 27 minus 1, which is 26. And the constants cancel out. So you get plus c minus c, and this is just 26. So the answer in this problem would have been 26. Is that making sense? So in general, and you see, so you see, like everything really just boils down to finding the antiderivative. Once you have the antiderivative, the problem just becomes evaluation. It's just plugging in. So I mean, that can be a little bit tedious, but it's not too complicated. So um, what you see happened here is like the constants, right? What's called the arbitrary constant plus c cancels out, and that will always happen when you are finding a definite integral, because the constant remains the same at the top and at the bottom, so they will cancel out all the time. So like that's actually like a way to check that you're on the right way, on the right track. Like when evaluating a definite integral, the constants that appear in the antiderivative formula go away. Since they appear at the top and at the bottom, or since they appear when you evaluate at B and at A. Is that okay? So whenever you find a definite integral problem and you are evaluating the definite integral, the constant of integration will disappear. That will always happen. Or like the constant, I mean, it's sometimes called the constant of integration, but it's you can think about it just as a constant of the antiderivative that does disappear. Okay. So now let me just give you a bunch of formulas for the antiderivatives, which is like a in the same way in which I gave you like a table for derivatives, I can now give you a table of antiderivatives, and that is kind of like the basic building blocks, like the Lego block for finding any other um, antiderivative. Formula for antiderivatives. So let's start with something concrete. Or again, like these antiderivatives sometimes are called indefinite integrals. So like in either name is fine. Okay. Like the first one is like the integral for or the indefinite integral for x to the n. So here that means like we're trying to find now we're trying to find here, put here like a function whose derivative is going to give you x to the n. And if you think about it for a little bit, it is again like the inverse process of taking the derivative. So when we were taking like the derivatives, we would drop the value of the exponent by 1. So we're doing the opposite. So the opposite of lowering the exponent by 1 should be increasing the exponent by 1. And then like again, you would have brought up the exponent as a multiplication, but the opposite of multiplying it by it would have been like kind of dividing by it. So okay, so you see, like what I'm claiming is that if you take something like this, and you find the derivative of this expression, you will get x to the n. Okay, so that's what this formula is saying. That the derivative of this quantity will give you x to the n. Is that making sense? I mean, for this formula to work, the only restriction that you have is that you cannot have like m minus m plus 1 becomes 0, right? Because then the denominator doesn't make sense. So here, the only thing that wouldn't work is for n has to be different from -1. But if n equals -1, it is kind of like finding the antiderivative for 1 over x, right? So what is a function? What is a function whose derivative was 1 over x? Maybe you remember this one. What's a function whose derivative was 1 over x? It was a natural log, good. The only thing that's kind of ambiguous here is that, when I write 1 over x, I may want x to be negative, and natural log of a negative number is not defined, but still, if you put like absolute values inside the natural log, that kind of fixes the problem. So actually, in the case that x had been negative, putting like an absolute, is putting an absolute value for x takes that into account and fixes the problem. So, like that's why the answer for the antiderivative for the indefinite integral has like an absolute value of x. But besides that, it is really like the formula that you have seen before. So when you compute this, like you can just think that x is positive, and that's why the derivative is 1 over x. When x is negative, this is ln of minus x, but you can check that ln of minus x also has like derivative 1 over x because of the chain rule. Okay. And then the other one is, what if you are doing the antiderivative of e to the x? So again, that means find the function whose derivative is e to the x. That one is easier because e to the x is its own derivative. So the answer here is just e to the x plus c. So again, this means that if you take the derivative of e to the x plus c, you get e to the x, which we know that to be the case. And then the others are like the other ones that you need to know for sure are the trigonometric ones. I'm putting here like ones that you really need to memorize. All the others, like we are going to find from these ones. So I'm just putting in this table like the essential ones that everyone I would expect to memorize at some point. So here you're finding a function whose derivative is sine. That has to be negative cosine of x, I believe. We had done that before. And then for cosine of x, you're trying to find the functions whose derivative is cosine of x. That was sine of x. I think we also said that before. Now comes like the some of the more complicated ones. So let's start with this one, which I think is maybe a little bit easier. Anyone remember which function has derivative secant square of x? What function had derivative secant square? It was the tangent, right? Like the derivative of tangent was secant square. So you should put here tan of x plus c. Then what was the function? Which function had um derivative okay, secant of x times tangent of x? Which function had derivative equal to secant times tangent? It was secant. And just two more. Good, we're almost there, I promise. Then it would be cosecant of x. Okay, so which function had derivative equal to cosecant of x squared? Sorry, cosecant of x squared. It was minus cotangent of x. And finally, which function had derivative equal to cosecant times cotangent? It was minus cosecant of x. Okay, oops. So these are the basic ones. Let me see if I can put, they'll fit into on the screen at once. Yeah, so these are the basic ones that everyone really needs to know of, for sure. Like, throughout your entire, all your math courses that you'll take, if you take more than Calc 1, definitely all of these are really useful to remember. There's some more that we can add later on, but for now, these are kind of like really the building blocks for everything else. And then the last three, which are kind of they're good to have like written out separately, is like the integral for a sum. This will be used all the time. So if you want to find the antiderivative of a sum, you can just find the individual antiderivatives, add them together. That just happens because that's the same is true for the derivative, right? The derivative of a sum is the sum of the derivatives. So it's kind of like a property that's inherited from the derivative property. The other one was like, what if you had like a constant times a function, right? Well, if you remember when we was a derivative, you could sort of take out the constant outside the derivative. Here it is the same for antiderivatives. So here like a is like a constant in this case. Okay, so that one is useful. And the last one, which again, this one kind of follows from the table, but it's useful. I mean, people will get confused if you don't write it out explicitly. So if you're just like integrating a constant, right? What's the integral of a constant? We're trying to find a function whose derivative is that constant. So the easiest thing to write is ax plus c. right? Because if you take the derivative of ax plus c, you just get a. So here a is also a constant again. And again, this one kind of follows from the others because, but it's kind of better to write it out explicitly. It can be more useful that way. Okay. So these other three are like the building. This kind of like are the rules that will allow you to mix together the earlier ones. So with these three plus the list from before, then we can start doing interesting stuff. Is that making sense? Okay, so now okay, let's take a break because when we come back, we will start doing like we'll do some examples where we find antiderivatives, and then we'll combine them with the actual problem of finding the definite integrals. But it's a good place to stop for people to digest, like so that you can digest these properties. So let's stop here, like take a 5 minute break, and then when we come back, we'll do some examples where we put all of these into use. Okay, so let's do some examples. First, just of finding antiderivatives, and then of combining that with like the actual problem of finding the definite integral. Well, we can do them both at once, actually. Okay, so here are some examples. First, like a warm-up one. So let's find. Okay, so we'll find the antiderivative for this function first, and then we'll find a particular value. So I want to find let's say I want to find this one. Yeah, let's see this. Okay, good. Yeah, I want to integrate it from 1 to 8. Okay, so it's two-step problem. Um, but again, if you have the answer for part A, the formula, the answer for part B is relatively straightforward. So what's happening in part A? So the first thing you can see, you notice is that well, there's like a number 3, which is like a constant. Again, you can always take the constant out of the antiderivative, so you can just write it as 3 times the integral of the x divided by x to the 2/3. Okay. And then once you have done that, you can just go to the list of integrals I gave you to see if this one is similar to any of the ones that I gave you before. So definitely it cannot be any of these because like these involve exponentials or trig functions and it's not 1/x. The only one that's kind of close to it is like x raised to some power. Okay, so we just have to rewrite it in that format. So how can you rewrite it in that format? In that version, it's like x to the negative 2/3. Yeah. So now it does look like x to the n. Is that making sense? So this is really like the integral of 3 times x to the n dx. And for that, you can use the formula that I gave you, which is, you have to be careful here, but the formula was add 1 to the exponent, because again, it's like the reverse of the formula for the power rule in terms of derivative. So add 1 to the exponent and divide by the new exponent, right? So that's what the formula said. And now you just substitute that for the values that we have. So n in this case, it's minus 2/3, right? So what's minus 2/3 plus 1? That's 1/3, right? So you get x to the 1/3 divided by 1/3. So here you also have to be careful because of the fractions plus a constant of integration. You get that is 1/3 becomes a 3 on the top, so you get 9 times the cubic root of x plus okay. So here you have 3 times a constant, so you can just write it as 3c, or I mean, it is common to, like, 3 times a constant is a new constant, so it's not unusual to just give this a new name if you want. So you could write that as 9 cubic root of x plus C tilde or C new. I mean, people don't worry too much about this per se. So like you could just, let's call it C new. But I mean, you could have left the answer this way or like this way. I mean, even people will relabel this C again, although that can be a bit confusing, especially the first times you're seeing it. But what I'm trying to say is that like the constant of integration, like what's called like the constant of integration, or this constant that appears in the antiderivative formula, the thing that matters the most is just to have one around at the end of the answer. It doesn't matter too much like how like the particular way in which it looks. So you could have left the answer this way, or you could have left it that way. Is that okay? But what's important is that then what this is saying is that the integral or the antiderivative of 3 dx over x to the 2/3 is 9 cubic root of x plus c. So again, what this means is that if you were to take the derivative of this function, you will find 3 over x to the 2/3. That's what that means. Is that making sense? And then for the antiderivative, for the definite integral, if you wanted to find the definite integral from 1 to 8 of this, what I told you you're supposed to do is evaluate this antiderivative at x equals 8 and at x equals 1 and subtract the answers. Oops, I may already evaluated it, sorry. Let me do an extra step. So you take the antiderivative. So you evaluate it at x equals 8 because 8 is the top bound. And you evaluate it at x equals 1 because x equals 1 is a lower bound. And then you get right 9 cubic root of 8 plus c new minus 9 cubic root of 1 plus c new. So what's the cubic root of 8? That's 2. So 9 times 2 is 18. and this is 9, because cubic root of 1 is 1, so you get 9 plus 15. So you get 18 minus 9, that's just 9. Is that okay? So that's the answer in this problem. Um, any questions about this? Okay, let's do another one. Mhm. Yeah, let's do 2 more, and then we'll do other stuff. Here's another example. Again, I'll break it into 2 pieces all the time so that this is more like a practice of both skills. So first part, let's say I want you to find okay. So maybe for part 1, which is the most important one, okay, I'll give you 2 minutes to think about it, and then we can discuss it. So let's 2, we can discuss what the answer should be. Okay, did anyone find the antiderivative for the first one? Correct. Good, good, good. Perfect. So the thing that you could do is break it up. So you should think about this as breaking it up. And again, then you compare, and this is natural log. That's like back in the table. And this is like the same as before, but with n equals 2. So it's like x cubed over 3 plus. Okay, now there's something here that I need to say as well. So you can think of the first antiderivative as giving you a constant. So you can call that constant C1. And then the other one gives you natural log of x, an absolute value, plus C2. So here you kind of can group the stuff that depends on x, that's the important stuff. And again, we get to this point, like this means like one constant plus another constant. That at the end of the day doesn't matter too much. So you can just like regroup them into a single constant. So call the sum C. And that's typically how the answer would be written. So you could also have left it in terms of C1 and C2. It just looks a little bit more messy. Okay. Is that making sense? And then again, it just follows from applying the integration rules separate, like the antiderivative integration or antiderivative rules for the sum. And then if you wanted for part 2, if you wanted to find the definite integral, like an explicit definite integral, what the rule says is that just take the antiderivative and evaluate it at the top, and take the antiderivative and evaluate it at the bottom and subtract. Okay, let's see. So at the top should be e cubed over 3 plus ln of e plus c. Comes at the bottom, 1 cubed over 3 plus ln of 1 plus c. Okay, and what do you get? Well, again, the c's cancel. That always happens. Then you get e cubed minus 1 over 3, which I don't know what that is, so I'll just leave it like that. And then you can put plus ln of e plus, but ln of e is 1, so you can put plus 1, and ln of 1 is 0. So I don't need this one as well. And then if you want, you can combine these together. So this is the answer. Okay, is that making sense? Okay, and now let me give you this one for you to think about. It is a little bit trickier because of you'll see what happens. But okay, now you get like, hopefully again, like this is the idea is one more time that only thing that matters is to find the antiderivative. Once you have the antiderivative, almost everything else is like just evaluating. So the real part of the problem is to find the antiderivative. So let me give you one, which is it has a trick. So if you kind of realize the trick is not too bad, but if you don't, then it can be confusing. So here's another example. Okay. So let's say I gave you that in in function, and I want to find the antiderivative of that. So try to think about what that should be. I mean, again, it can be easy if you know what to do, but otherwise it can be a bit confusing. So let me give you this one a little bit more time. I'll give you 4 or 5 minutes to think about it, and once we come back, we'll discuss it together. Okay, so what did you end up doing, and what was the idea here? And anyone was able to figure it out, or what could you do to find this one? So this one requires a little bit of it is tricky just because of the way in which it's the function is written. What you had to do was to split. Well, first, like you can take out like the 3 if you want, so you can put like 1/3 outside of everything. That's not like a huge thing, but can be useful. Just makes it look a little bit better, and also it's more suggestive of what you're supposed to do next, which is just to break it into pieces. So x cubed over x, that's x squared. Then 2x squared over x is 2x, and then x over x minus 1, right? And now this does look a lot better. Is that making sense? Like, and again, you can break it into now separate integrals. Oh, in fact, it's easier, it's better to leave the 2x here inside. And now it's the same as before. So x squared, like the integral of that is x cubed over 3 plus a constant. Then what function it gives you a derivative equal to 2x is like x squared, like, so you can put x squared plus another constant, and one integrates. This looks a little bit odd, but what's the integral of the x? If you want, you can write it as 1 dx. So we're just trying to find like a function whose you know whose derivative is 1, and that is x. So in fact, what I'm doing here is oops, just to go up, sorry. What I'm doing here is like this formula, but here a equals 1. So this one gives you minus x. And again, minus a constant of integration, a minus because there was a minus in front of everything. So that's what it gives you. And again, if you were to take, it looks a little bit complicated, but if you put the 1/3 and then you
put everything with x first, it looks a lot better. So what I'm saying is that if you take the derivative of this stuff, you will get x squared plus 2x minus 1. So that's why it is the correct formula. It's just that, again, it is kind of weird to, you know, to have like this C1 plus C2 minus C3 around. So what you can do is just call that C. And there's also like a 1/3 that you can reabsorb here. So you can just write this as 1/3 x cubed over 3 plus x squared minus x plus C. And that's typically how you would write that. Is that making sense? Okay, now we come to the last step of that, like the last trick for finding antiderivatives, which is called the U sub method. And that's like the most important method, the most complicated method. So we'll spend a little bit of today and a lot more tomorrow just doing this. So I want to like start here today with just like some warm up exercises, because the U sub method is kind of like the opposite of the chain rule. And if you remember, the chain rule was kind of confusing, so the U sub method, it will be confusing as well. So we're going to talk about the U sub method. And again, it's kind of like the reverse of the chain rule. Okay, so let's start with an easy thing, okay? So imagine here's a baby example. And again, tomorrow we'll do a lot more complicated, but it's good to build it up. So imagine that I gave you something like cosine of 2x dx, right? So what's the problem with this indefinite integral or antiderivative? The problem is that if you go back to the table that I gave you, right? If you go back to the table that I gave you, we have the answer for cosine of x, right? But we don't have the answer for cosine of 2x, right? Now there's a 2 inside the cosine, right? So that cannot be attacked directly, right? So the problem now is this 2 inside the cosine. That's what is giving us issues. So in the U sub method, it's kind of like wishful thinking, where you kind of just force it to look like before, right? So what would be the way to force this into looking exactly like before? The way to do that is by making a change of variables, okay? So this is why this is called the U sub method, because you would make a change of variables. So what would be a good change of variables to make here? And also think about like the chain rule. What, like, if you saw something similar to this, what sort of like, what could be called U in this case? What would that make sense? Yeah, it would make sense to call U 2x. Okay. So if you do that, then you get to cosine of U, right, times dx. Okay. Which is correct. This is correct because you did nothing weird here. It's just that it looks a little bit odd because like you're combining something that has a variable u with something that has like the variable x. So you kind of have like a strange hybrid which you're not allowed to have. So you have like here like some sort of hybrid, which uses u and x at the same times, right? Which is using two different variables. And if you look at all the other integrals we have done, it has always have been like with the same variable. It didn't matter too much that this variable was called x, but what did matter was that, you know, there was like a consistency in the variable. There was no other variable that appearing here. So, but there's like an easy fix for that, which is why this this other notation for the derivative is very, very useful. So it kind of saves a day here, because if you think about this change of variables, right, u equals 2x. So if u equals 2x, you can say that the u dx is 2, right? That makes sense. And you kind of do something that looks a little bit odd, but it actually ends up working. So if you divide both sides by 2, you get 1/2 the u dx equals 1, right? And that gives you, if you multiply both sides by the x, that would give you like an equation for the x. So you could say that 1/2 of du equals the x. Okay. And that is giving you like actually something to replace the x with in terms of the u. So if you go back to the integral, you would get cosine of u times the x, but now the x is du over 2. Is that making sense? But the advantage of putting it in this format is that everything now has like the variable u. Like again, we'll do some more examples to get used to this idea. But if you get this, like essentially you will get the main idea in all the substitution problems. It's just always making a u variable, change variables. That kind of looks like the same of change of variables that you would have done in the chain rule problem, but now it's kind of working in reverse. Because if you do that, like then the 1/2, you can take it outside the integral. So you get cosine of u du. And now this is easy because it's now just finding a function whose derivative is cosine of u. And this is literally the same antiderivative as before, right? We did have this in our list of antiderivatives. It's just that it was with a different letter, but that's more like of a translation problem. So now because there's an u here, like the answer should just be in terms of u. But that doesn't like, it's not like a significant difference. So the answer here becomes 1/2 sine of u plus a constant. Okay. But it's kind of like the same as we would do before. Like you are not, u was kind of like an auxiliary variable, so it was not really inside the problem. So what you can do is just reverse back to the original variable, so you get u sine of 2x over 2 plus the constant over 2. Okay. So what I'm claiming is that the integral of cosine of 2x dx is sine of 2x over 2 plus some constant. Is that making sense? And again, the good thing about these antiderivatives is that you can always check them. So if you were not sure if this is the answer, you could take it the derivative of this to check whether you get a cosine of 2x, and you do. So that means that it had to be the correct answer, the correct antiderivative. Is that okay? Is that making sense? So far, so good. Okay, let's do one more today. Because I have been giving you a lot of information so that tomorrow we can just start this again with a fresher mind. So where is my, oh, here it is. Okay, let's do another one. And again, tomorrow we'll do more complicated ones and I'll tell you what the method of substitution is. So here's another example. Imagine that you wanted to find that, right? So the problem, I mean, this is a lot more confusing. Because like we don't have anything really for like combining, like, you know, we don't have anything among our rules that deals with an exponential and x at the same time being multiplied, right? uh but like a good rule of thumb is kind of try to find a substitution that simplifies like what like a trigonometric expression or like an exponential or like a not like logarithm. So here what you should go for is to try to find like a substitution that makes the exponential easy as possible. So in general, like let me write that as a hint. You should try a substitution which makes the exponential or the logarithm or the strict functions as simple as possible. Okay. So what would make the exponential as simple as possible in this case? What would be the change of variables? So the change of variables should be u equals x squared, okay? Because that will make the exponential just look like e to the u, okay? So once you get to this point, you could try to replace this in terms of u, but it's better just to wait and see what happens with the x. So let's try to see what happens with the x here. So again, like the idea in all these change of variable problems is to do the same as before. So if you take the derivative of the u with respect to x, of u with respect to x, you get 2x. And then if you multiply both sides by the x, you get that the u equals 2x dx. You see? But that's nice because if you look at what we had before, we had like this expression, right? So 2x dx did show up in this expression before. That's essentially what we meant by du, according to the change of variable formula. So this is going to be 2x dx becomes du, and e to the x squared becomes e to the u. Is that making sense? So again, that does this is why this one is tricky, because you do have it's a lot less obvious than the ones we have been doing before, because you kind of have to think about like a kind of like chain rule problem in reverse. But if you get to this point, like once you get to the right substitution, everything is a lot more mechanical. Because the idea is that you can then compare it to like an integral that you knew before. So the integral for e to the u, if you remember that, it was e to the, I mean, the integral of an or the antiderivative of an exponential is just the same exponential. So there's nothing here like weird going on, but it's more like, you cannot leave the answer in terms of like u, because u was an auxiliary variable. So it just gives you e to the x squared plus c. So what I'm trying to say is that if you were to integrate this, you would find e to the x squared plus c. Because the derivative, another way to say this is that the derivative of this function with respect to x will give you that. Okay. And again, if you had tried to find the derivative of this function with respect to x, you would have done a u sub that or a change of variables where u equals x squared. So that's kind of like the same change of variables that we're doing here. It's just that we're playing with it in a slightly different way because now it's like inside like an integral and not as a derivative. Is that making sense? So again, these are way more confusing. And I feel like I've given you too many things today. So what I want to do tomorrow I want to do a lot more examples about the use of, like the use of is really the last topic in terms of tools for finding integrals. So if we do the use of correctly, it is like, it's one of the, as I said, there are not that many topics left for the exam. I'm actually pretty sure we'll finish all the material by Thursday of this week. So yeah, I think I only need 2 more classes tops. So yeah, let's end here today so that you can absorb all this material. And as I said, I'll finish grading the exam today. I'll send you an announcement about that, post the solutions, give you some information about that. And I'll also send you the information for the quiz on Thursday today so that you have more time to practice for it. So I'll do that in a couple of hours. You too, you too.